Welcome back to the deep dive. We've got another really interesting set of sources lined up for you today.
Yeah, looking forward to it.
Our goal, as always, is to pull out those key insights so you get the core knowledge without getting buried in the details.
Exactly.
Today, we're diving back into, well, the really cutting-edge stuff. AI, informal mathematics. We're looking at DeepSeek Prover V2. If you were with us for the deep dive on DeepSeek R1 and V3, this is the follow-up. The next chapter.
That's right. And we're here to break down what's actually new, what's changed, and, why it's a pretty big deal.
Yeah, because, AI doing formal math proofs, it can sound a bit abstract, maybe even dry.
It can seem that way, sure.
Yeah.
But its importance is, well, it's definitely growing. We're talking about AI getting involved with math at a really fundamental level.
Constructing proofs, right. The kind of rigorous logic that underpins science and tech.
Exactly that. And DeepSeek Prover V2, it brings some genuinely new ideas to the table for how to do that. We should see some aha moments today.
Okay, let's get into it then. DeepSeek Prover V2. What's its main job? Its core purpose?
Okay, so at its heart, DeepSeek Prover V2 is an open source large language model, but it's specifically built for one thing: formal theorem proving.
And it uses something called Lean 4.
Correct. Lean 4. Think of it like a programming language, but for mathematical proofs, it's incredibly strict. A computer checks every single step for logical soundness.
Like a super strict compiler for math logic.
That's a good way to put it, yeah. And DeepSeek Prover V2 is designed to operate within that really precise, rigorous system.
So V2, what's the leap forward here compared to, say, V3 that we discussed before? What makes it different?
I'd say the most really groundbreaking part is this new training method they call a cold start procedure.
Cold start. Okay, that sounds intriguing. How does that work? How do they kickstart this model?
Well, it's pretty clever. They use the previous model, DeepSeek V3, to generate the initial training data. They basically asked DeepSeek V3 to take complex math problems and break them down recursively into smaller, much more manageable pieces or subgoals.
Right, okay. Like tackling a huge jigsaw puzzle by doing the corners and edges first. Makes sense. Break it down.
Exactly. And once DeepSeek V3 figured out how to logically prove these smaller pieces, it then synthesized these proofs. It stitched them together into a kind of connected reasoning sequence, a chain of thought. But here's the really key part. This chain also included DeepSeek V3's own more general, maybe less formal reasoning about the problem.
Oh, that's fascinating. So you're not just getting the formal steps, you're getting the intuition almost, the higher level thinking from the general LLM blended with the strict Lean 4 proof structure.
You've got it. It's like combining that broader reasoning ability with the absolute rigor needed for formal proof.
Wow.
And this data, this mix of informal thinking and formal proof steps, became the foundation, the cold start data for training DeepSeek Prover V2.
So they're bootstrapping it, using the general model smarts to teach the specialized model how to not just write the formal code, but how to think mathematically in a way that leads to it.
Precisely. It's a really efficient way around a major bottleneck in training these specialized AI. It learned the formal language and the problem-solving approach.
Super ingenious. Okay, so the model itself, DeepSeek Prover V2, you mentioned it's big. What are we talking about scale-wise?
Yeah. The main one they highlight is DeepSeek Prover V2 671B. That 671B stands for 671 billion parameters.
Billion, okay.
Yeah. So parameters are like the knobs inside the AI that get tuned during learning. More knobs generally means it can learn more complex stuff. 671 billion is definitely up there with the really powerful large language models.
And does that translate to performance? What can it actually do with all that power?
It seems so. On a benchmark called Mini F2F test, which is tough, specifically designed for formal proving, the 671B model hit an 88.9% success rate. That's with a lot of attempts, mind you, but still very high.
Yeah.
And on another benchmark, PutnamBench, which uses problems from the notoriously hard Putnam undergraduate math competition, it solved 49 out of 658 problems.
Putnam problems. Wow, okay. That is serious mathematical ability.
It really is.
And the sources mentioned a new benchmark they introduced too, ProverBench.
Yes, exactly. ProverBench. It's a new set of 325 formalized math problems. They created it to get a richer evaluation of these models.
That's special about it.
One particularly interesting thing is it includes 15 problems directly from recent AIME competitions.
AIME. the American Invitational Mathematics Examination.
Sure.
Those are really hard high school contest problems.
Extremely hard. And DeepSeek Prover V2, the 671B model, it solved 6 out of those 15 AIME problems formally.
Okay, 6 out of 15, how does that compare?
Well, for context, they also tested the original DeepSeek V3 on those same problems, using its more general informal reasoning. V3 solved 8 of them, using a kind of majority vote from multiple attempts.
Ah, interesting. So V3, with its more intuitive approach, still edges it out slightly on those specific problems. But V2, working strictly within the formal proof rules, is getting really close.
Exactly. That gap is narrowing. It suggests AI isn't just pattern matching symbols anymore. It's getting closer to a kind of, well, understanding that aligns with human intuition, even within that super strict formal system.
Yeah, that bridge between intuitive reasoning and formal logic seems key. Okay, let's go a bit deeper into the how. You mentioned recursive proof search via subgoal decomposition. Sounds central.
It absolutely is. It's the core technique. Like we discussed with the cold start data, the main idea is breaking a big, complex proof down.
Into smaller steps, lemmas, right?
Precisely. Intermediate lemmas are stepping stones you need to prove to get to the final result. So recursive proof search sounds complex, but yeah, it's about breaking it down, solving the pieces, putting it back together.
And how does V2 actually manage that breakdown?
So the process uses DeepSeek V3 again, actually. V3 does the initial subgoal decomposition. It sort of sketches out a high-level plan for the proof.
Okay, so V3 is the strategist.
Kind of, yeah. It identifies the key intermediate steps. Then these steps get translated into formal lean-for statements, sometimes with placeholders saying, okay, prove this bit now.
So V3 gives the roadmap. Then what finds the actual proof steps for those smaller bits?
That's where a smaller model comes in, a 7 billion parameter model. Still big, but much less computationally heavy than the 671B monster.
Right.
This 7B model does the detailed proof search for each individual subgoal. It's a division of labor, keeps the computation manageable.
So the big model plans, the smaller model executes the details for each step.
That's the gist of it. The 671B model is involved too, especially in the COP mode we'll get to, but the 7B model handles a lot of the specific search within subgoals. It's efficient.
Makes sense. Use the right tool for the job. Now, what about curriculum learning? How does that fit in?
The subgoals are key there too. The system uses these broken down pieces to generate sort of practice theorems. They start simple and get progressively harder.
Ah, like learning levels in a game.
Exactly. It guides the model's learning. Master the basics and move up. It's a structured way to learn this very complex skill.
Sounds like a very thoughtful training design.
Yeah.
Now, the paper talks about unifying informal reasoning and proof formalization. We touched on this, but how does it really work in the system?
It really comes down to that two-stage process we've been outlining. You have DeepSeek V3 providing the high-level composition, the sort of informal strategy.
The roadmap.
The roadmap, yes. And then you have the prover models, like the 7B one, focusing on constructing the detailed formal proof steps for each part of that map. It inherently blends the strengths of both worlds.
Okay. Now, the sources compare this to something called Kamina Prover, especially regarding the synthetic data generation. What's the difference there?
Yeah, that's an important distinction in approach. DeepSeek Prover V2 takes these, let's say, natural language-ish proof outlines from V3 and formalizes them, right? Building the detailed formal structure.
Right, sketch to formal proof.
Kamina Prover does the opposite, in a way. It takes completed formal proofs and tries to work backward. It tries to reconstruct the plausible natural language reasoning, the intermediate thoughts that might have led to that final formal proof.
Huh. So one builds down from the sketch, the other tries to reverse engineer the sketch from the finished building.
That's a great analogy, actually. Yeah. DeepSeek goes sketch to formal. Kamina tries formal to implied reasoning.
Interesting difference in philosophy. And then there's reasoning-oriented reinforcement learning.
Yeah.
How does that fine-tune the model?
So after the initial training with that synthetic data, they use reinforcement learning. Basically, the model tries to generate a proof.
It gets feedback.
Exactly. The main feedback is simple. Did the lean-for proof assistant verify it? Yes or no? Correct or incorrect?
Straightforward, pass-fail.
Very direct feedback. But they found something interesting. Sometimes the model's final proof structure didn't quite follow the plan, the subgoals laid out by V3 initially.
It found a different way.
Maybe. Or it just didn't use the intermediate steps properly. So they added another reward signal, especially early on, a consistency reward.
What did that do?
It encouraged the model to actually use those decomposed lemmas from V3's plan in its final proof. It penalized proofs that didn't stick to the intended structure.
So making sure it follows the strategic roadmap, not just finding any path to the end. Especially for complex proofs where those steps are needed.
Exactly. It reinforces the intended reasoning path.
Okay, now let's unpack the two-stage training details. You mentioned non-CoT and CoT modes. What's the difference?
Right. So the training creates two ways the model can generate proofs. First is the high-efficiency non-chain of thought mode, or non-CoT.
Non-CoT sounds like speed.
Speed and conciseness. It aims to generate the final formal proof quickly without necessarily showing all the intermediate thinking, like just giving the answer in math class.
Got it. Straight to the point.
Yeah.
And the other mode, high-precision chain of thought. CoT.
CoT, yeah. As the name suggests, this one is all about transparency. It explicitly lays out the steps, the reasoning, the logical flow within the proof structure.
Showing your work.
Exactly. It's about the why and how, not just the final what. So non-CoT for efficiency, CoT for detailed, verifiable reasoning.
And how are these trained differently in that two-stage process?
The first stage focuses on training the non-CoT model. They use something called expert iteration, combined with that curriculum learning we talked about based on the subgoals. It allows for faster training cycles.
Okay.
Then the second stage trains the CoT model. This stage heavily uses that cold start data, the stuff combining V3's reasoning with the synthesized proofs. And this CoT model is further refined using reinforcement learning.
So a dedicated process for each mode. Seems very structured.
Yeah.
Okay, let's talk results. Mini F2F benchmark, you said 88.9% pass rate. How does that stack up against others?
It's currently the new state-of-the-art on Mini F2F test. That 88.9% was with a large sample budget, 800 and 192 attempts. Even with just 32 attempts using the CoT mode, it hit 82.4%.
And the competition. Models like Hypertree, InternLM, Camino Prover.
Yeah, when you compare it to those and others like Hunyuan Prover, BFS Prover, Linabel, Gödel Prover, STP, DeepSeek Prover V2 671B comes out on top, often significantly.
Even considering model size and how many tries they get.
Generally, yes, it's really pushed the boundary there. And interestingly, even their smaller 7B model is extremely competitive against other open source provers, often beating larger ones.
Right, the 7B model holds its own. And you mentioned the gap between the 7B and 671B widens with more attempts.
Yeah, the data shows that. Give them more chances to find a proof, and the bigger model pulls further ahead. It suggests the 671B can better utilize that extra search effort on the harder problems.
Makes sense. And did they break down performance by the type of math problem, like algebra versus geometry?
They did. On Mini2F, the 671B model does consistently well across the board. Olympiad problems, AM, AMC, general math categories. It seems particularly strong in algebra and number theory within the math set.
Okay. And CoT versus non-CoT performance?
CoT's mode consistently gets higher accuracy, more problem solved. But the trade-off is the output is much, much longer because it includes all that reasoning.
Right, the detailed steps.
Yeah. Although one curious thing, the researchers noted that the big 671B model, even when running in the supposedly concise non-CoT mode, sometimes still included little natural language comments in its output.
Really, like notes to itself.
Almost, like its internal chain of thought was sort of leaking out a bit, even when it wasn't supposed to be explicit, suggests some implicit reasoning happening under the hood.
Huh. Fascinating. Okay, moving up in difficulty. Undergraduate level. ProofNet and PutnamBench. How did you do there?
On ProofNet, which has a wider range of undergrad topics, again, the CoT reasoning provided a significant boost in performance. It shows the model can generalize beyond its main high school level training data.
Good sign for broader applicability.
Definitely. And on PutnamBench, those super tough problems, the 671B model solved 49. Again, the CoT version significantly outperformed the non-CoT one. Really shows CoT's value for complex, multi-step reasoning.
And wasn't there that weird finding with the smaller 7B model on Putnam?
Yes. That was really interesting. The 7B non-CoT model actually solved 13 problems on Putnam that the larger 671B model didn't solve.
How?
It used some specific tactics related to finite sets and cardinality, using things like cardinal.to-nat, that just weren't present in the bigger model's successful proofs.
Wow. So the little guy found a clever trick the big one missed. A good reminder that scale isn't everything. Sometimes different approaches yield unique results.
Absolutely. It highlights just how complex and, frankly, sometimes surprising the learning process in these models can be.
Okay, last benchmark area. ProverBench in more detail. We know about the AIME problems. What about the textbook formalization part?
Right. Besides the AIME problems, ProverBench includes 310 problems sourced from high school competition materials and actual undergraduate textbooks.
So a broad range of topics.
Very broad. Number theory, algebra analysis, abstract algebra, functional analysis. A real mix. And across this diverse set, the DeepSeek Prover V2-671B model, especially with Cut A reasoning, consistently performed best.
So it confirms its strong capabilities across different mathematical domains and difficulty levels.
It really does. It's robust.
Okay, so wrapping this all up, DeepSeek Prover V2 feels like a genuinely significant step forward.
I think so, yeah.
The performance gains are clear, especially on tough benchmarks.
Yeah.
And this whole cold start training, blending the informal reasoning from V3 with the formal proof generation. That seems like the key innovation here.
Absolutely. That, combined with the structured proof search, the curriculum learning, the reinforcement learning, it's a very well thought out system for tackling this incredibly hard problem.
Bridging that gap between human-like mathematical intuition and machine-checked formal rigor.
That's the core challenge, and they've made real strides. These advancements are definitely important for the whole field of automated theorem proving.
And the fact that it's open source is huge too, right? Allows others to build on it, experiment.
Definitely. Openness really accelerates progress. For anyone listening who wants to get into the nitty-gritty, the GitHub link in our sources is the place to go.
Yeah, check that out. So thinking ahead, where does this go? Is AI going to be discovering new math soon? Tackling things like the IMO problems consistently?
Well, that's the million-dollar question, isn't it? It's hard to say definitively, but the trajectory is certainly pointing towards AI playing a much bigger role. Maybe not pure discovery yet, but definitely in verification, exploration, and assisting mathematicians. Tackling the hardest problems, like IMO level, is still the grand challenge. But DeepSeek Prover V2 shows we're making impressive progress on that path. It builds nicely on what they did with R1 and V3, showing real iterative improvement.
An impressive stride indeed. Lots to think about there.